Okay, hello everyone in a new video. So we have reached part 4 of chapter 7, which is Newton's second law for grade 11 students. Now in this part we are going to solve some exercises and we are going to introduce the notion of dynamics. So let's start with exercise number 5. They are telling me a solid S of mass m is equal to 100 grams rests on a smooth inclined plane. So let me say that the mass of the solid is equal to 100 grams, knowing that the grams is not the SI unit of mass. In order to convert from grams to kilograms, we divide by 1000. Now they are telling me that it rests on a smooth inclined plane, and by this they mean that this plane is very smooth, such that the friction between S and this plane is neglected, so no friction. Okay, so in this case smooth means no friction. Then S is connected to a support by means of a light and extensible string, and the word inextensible means that the string is always stretched. It means that the tension is being transmitted equally at both ends of the string, such that it makes an angle beta. Beta is equal to 30 degrees. With respect to the inclined plane, as shown on the adjacent figure, take G is equal to 10 meters per second square, which is equal to 10 newtons per kilogram. Now in number 1, they are telling me to name and represent the external forces exerted on us. So in this case, we need to redraw the figure, but first let's name the forces that are exerted on us. So because the solid S has a mass, then it will be directly subjected to the weight W. Because here we have a string, then it will be subjected to the tension T. And because we have a support, then it will be subjected to the normal reaction R. So we have the normal reaction R. So sometimes this force is referred to an vector. Now, the physical definition of the weight, it is the force exerted by Earth on us. The physical definition of the tension, it's the force exerted by the string on us. And the physical definition of the normal reaction, it is the force exerted by the plane on us. So let me draw the inclined plane. So this is the box, this is the solid S. And this is the horizontal, the line parallel to the support, and this is the string that connects the solid S to the other support. Okay, so here, because we are interested later on in determining the magnitudes of the forces, which means that we will apply Newton's second law, so let me write here the different steps that we usually follow in order to determine the magnitude, and they are given by. So step number 1 is to list the forces. Step number 2 is to choose a reference system. Step number 3 is to project the forces. And step number 4 is to use sum of forces is equal to MA. and project the equation. So this is the solid S, this is the angle beta, and this is the angle alpha. We have here that alpha is equal to 45 degrees and beta is equal to 30 degrees. So let's represent the different forces acting on the solid S, because they told me represent, and here because they didn't mention with a scale, so we will just represent them. So suppose that this is the point of contact between the string and the solid. This is the center of gravity of G, and this is the point of contact between the support and the solid S. We have the weight which is acting vertically downward like this. We have the tension which is always along the string. So recall that always the line of action of the tension is along the string, and the line of action of the normal is perpendicular to the support like this. The point of application is the point of contact between the two bodies, and we know that always the normal reaction is toward the object like this. So now we are in number 2, done for part 1. They are telling me determine the magnitude of the force exerted by the string on S. So here they are referring to the physical definition of the force. So it is the tension which is the force exerted by the string on S. So we are interested in determining the magnitude T, and this done by applying a Newton's second law, which is given by this. Now notice that we are done with the step number 1. Now let's choose a reference system. In this case, we will choose the reference system to be like this. So always we start by taking the x-axis parallel. So always whenever we have an inclined plane, we take the x-axis to be parallel to the inclined plane. Now notice that I have chosen the positive direction to be like this and not this, because if the string is cut, then the solid S will slide along the inclined plane. Okay. Now as for the y-axis, it will be chosen to be perpendicular along the x-axis, and the point of intersection will be simply between the x-axis and the y-axis, which is this. So this is the origin O, and this is the positive direction of the y-axis. So we are done with step number 2. Now let's project the forces. Let's start by the force, which is the weight. And now before we start projecting the forces, let's indicate the different angles. So if this is beta, then this angle here. So recall that the tension T is a free vector, then T can be moved. So this is the point of application of T. So the T vector can be moved from this point to this point, which is the origin O. So in this case, this angle is given by pi by 2 minus beta, which is the same angle that T makes with the y-axis, because recall that the vector T is a free vector, it can be moved from this point to this point. Now if this is alpha, then this angle is pi by 2 minus alpha, and because this line is parallel to this line, so this angle will be also pi by 2 minus alpha. So if this is pi by 2 minus alpha, then this angle is alpha. So now we are ready to project. So Wx, the x component of the, so notice that any vector A can be expressed as Ax multiplied by the unit vector I plus Ay multiplied by the unit vector J. Now we are determining the x component and the y component of all three forces. Now Wx, notice that Wx is pointing in the same direction of the x-axis, so it's positive. So Wx is positive, and its magnitude is given by W, and the cosine, and we multiply by the cosine of W between W and the x-axis, which is pi by 2 minus alpha, so cosine pi by 2 minus alpha, and this will give us W sine alpha. Now as for Wy, so Wx is equal to W sine alpha, And wy, notice that w is pointing in the negative direction of the y-axis, so it's negative, multiplied by w by cosine of the angle between w and the y-axis, which is alpha. Just give me 1 second. Now, as for the force T, let me use the same notation. This is the vector R. So Tx, notice that T is pointing in the negative direction of the x-axis, so it's minus T of cosine beta, since beta is the angle between T and the x-axis. And Ty will be plus, because it's pointing in the positive direction of the y-axis, T cosine of pi by 2 minus beta. So this is equal to T sine beta. Then this is Tx is equal to minus T cosine beta, and Ty is equal to T sine beta. Now, as for the force R, then Rx, notice that R is completely lying along the y-axis, so Rx is 0. As for Ry, it's plus R, because it's pointing in the positive direction. Now we are ready to apply Newton's second law, which is given by sum of forces is equal to ma. So what are, let me say, apply Newton's second law for us. Or we can say that because the solid S is at equilibrium, here they mentioned the equilibrium. Okay, although they didn't mention the equilibrium, but notice that the solid S cannot move because it's attached to the string. So here it is at equilibrium. So let me say at equilibrium instead of applying Newton's second law. And here we are applying the condition of equilibrium for body S. So we say that the sum of forces is equal to 0 vector. Notice that the vector must exist on both members. Now, what are the different forces acting on the solid S? We have the weight plus the tension plus the reaction, which is equal to 0 vector. Now, this is a vectorial equation consisting of 3 vectors. How do we solve this equation? We need to project along the x-axis and along the y-axis, so we are also done with the step number 4. Now we are interested in determining the magnitude of the tension T, and as for part B, the magnitude of R. So notice that now T, the magnitude T exists in both components, the x component and the y component. So first let's start by the x component. So let's say projection along the x-axis. Now in this case we drop all the vectors, and each vector quantity will carry the label x. So here we have wx plus tx plus rx is equal to 0. Now wx is given by w sine alpha, tx is given by minus t cosine beta, and rx eventually is given by 0. Now the values of alpha and beta are given respectively to be 45 and 30 degrees. Alpha is equal to 45 degrees and beta is equal to 30 degrees. So we know the values of sine alpha, cosine beta. What about the weight? We have that the mass is equal to 0.1 kilogram and the value of the gravitational field strength is 10 in the SI. Then if mass is equal to 0.1 kilogram, then the weight, which is equal to m multiplied by g, which is equal to 0.1 multiplied by 10, which is equal to 1 in Newton. So we have also the weight, so the only unknown is given by t. So what's the type of this equation? This is a linear equation and one unknown. So always you know that the vectorial equation gives the birth of two linear equations, okay? Now, so this is the value of W is 1, sine alpha is given by sine 30, minus t kept as an unknown with cosine, alpha is 45, minus t is kept as an unknown, cosine 30 equal to 0. Then solving for t, we obtain that the value of t is equal to sine 45 divided by cosine 30, which is equal to square root 2 over 2 divided by half. Now this is equal to radical 2 newtons, so the value of t is equal to radical 2 newtons. And let me check this value on the calculator. Sorry, cosine, let me check. So sine 45 is equal to radical 2 over 2. Cosine 30 is radical 3 over 2 because it's the larger angle. So this is equal to, radical 2 over radical 3, and if you consider the conjugate and rationalize, then the answer is given by, so if you multiply by radical 3 and radical 3, so this is equal to radical 6 over 3 newtons. Then the magnitude of t in the SI is given by radical 3 divided by radical 6 divided by 3 newtons. This is it for part B. Now for part A, now in part B they are telling me the force exerted by the plane on S, and here they are referring to the normal reaction. So and this can be determined by the projection along the Y. So part B, let's reconsider the initial vector equation, which is given by W vector plus T vector plus R vector is equal to 0 vector. And now let's do the projection along the y-axis. In this case, we drop down all the vector quantities, and each vector quantity will carry the label y. Now wy is given by minus w cosine alpha as for ty, it's given by t sine beta, and plus ry is given by plus r, this is equal to 0. Now the value of w is given by 1 newtons. The value of cosine alpha, so alpha is equal to 45 degrees and beta is equal to 30 degrees, and the value of t is equal to square root of 6 divided by 3 newtons. Now in this case, we know the value of w, we know the value of this and this, the only unknown is r. So we place r in a box. What's the type of this equation? Linear equation and one unknown. So r is given by w cosine alpha minus t sine beta. This is equal to 1 multiplied by cosine of 45 minus t, which is given by radical 6 divided by 3 sine 30. So this is equal to radical 2 divided by 2 minus radical 6 3 times sine of 30 is given by half. So this is equal to radical 2 over 2 minus radical 6 over 6. So its ohm is given by 0.3 newtons. Then the value of R is given by 0.3 newtons. Okay. And the value of T in the decimal form is given by 0.82 newtons. Then this is it for this exercise. Now let's move to the other exercise, which is exercise number 6. Now they are telling me 3 light and inextensible strings are joined to a massless node A. So here the strings that we have that are given by S1 and S2 and S3 are inextensible, which means that they transmit tensions at both ends. So we have the node A, the mass of the node A is given by 0. A block S taken as a particle of mass m is equal to 0.2 kilograms is hanged from the string S3. The magnitude of the tension in S2 is T2 is equal to 2 newtons. And take G is equal to 10 meter per second square, which is equal to 10 newtons per kilogram. Now number 1. Calculate the weight of S, then deduce the magnitude of the tension T3 in S3. So which means that we are dealing with the Newton's second law because we are dealing with the magnitude of the forces. So let me write here on the scratch the different steps that we follow in order to determine or to how to deal with the Newton's second law. So step number 1 is to list the forces, and step number 2 is to choose a reference system. Step number 3 is to project the forces, and step number 4 is to write sum of forces is equal to MA and project. Now here we must be very careful because we have two bodies that are involved in the system. We have the body A and we have the body S. Okay, so we can apply sum of forces is equal to MA to body S and to body A. So notice that in part 1 they are telling me calculate the weight. So it consists of two parts. This is the first part. They are telling me to calculate the weight of S. So in order to calculate the weight of S, we can think about the Newton's second law, but notice that in this case we have the mass, which is given by 0.2 kilograms. So, and the value of G is equal to 10 newtons per kilogram. And by calculate the weight, they are simply asking me about the magnitude. So W is equal to ms multiplied by G, which is equal to 0.2 multiplied by 10, which is equal to 2 newtons. Okay, so the value of W is equal to 2 newtons. Now in the second part, they are telling me then deduce the magnitude of the tension T3 and S3. So, and by deduce it means that we need to use the previous part. So here, because, okay, so we determined the weight of S, which is vertically downward, and they are telling me deduce, it means that we need to deduce the tension T3 and S3 from the weight, okay? And the weight is being applied on S, so we are interested in the condition of equilibrium. So notice that this is at equilibrium because for sure the system is not moving. So it means that we need to apply the condition of equilibrium for the solid S. Now let's list, so we need to follow these steps. Let's list the forces that are acting on W. We have the weight W, and we have the tension T3 along the string S3. So we are done with step number 1. Now let's refer to step number 2 in order to choose a reference system. So suppose that this is the box. S, Here we have the tension, which is vertically upward like this, and we have the weight acting from the center of gravity because it's a force acting from a distance. This is the weight. This is string S3. Along the string we have the tension T3. And now let's choose a reference system. This is T3. We are only applying the condition of equilibrium for S, so no need to consider the point A. Then the reference system in this case is chosen in the following way. This is the x-axis, say for example positive direction, and this is the positive direction of the y-axis. And we are interested in determining the magnitude T3. We are done with step number 2. Now notice that in this case, if we write the condition of equilibrium, which is given by at equilibrium for body S, now sum of forces is equal to 0 vector, so we have the W plus T vector is equal to 0 vector. This equation only consists of 2 vectors, so no need to deal with it using projection. Whenever the vectorial equation it consists of 2 vectors, we can directly solve it. So moving T to the right hand side, it will gain a minus sign, then it will be W is equal to minus T vector. Then directly we can say in magnitude, this is T3, that now we drop down the vectors and we remove the minus sign, so W is equal to T3, but the value of W that we have calculated previously is given by 2 newtons. Then the value of T3 is equal to 2 newtons. So we have determined the magnitude of T3 it's given by 2 newtons. So T3 acting on S3 is given by 2 newtons. Let me make some space here. Now in number 2, they are just telling me represent the forces acting on the node A. So there are some parts missing from this exercise, but it's okay. So we are interested in representing the forces acting on the node A. So the node A is connected to 3 strings, and they are given by S1, S2 and S3. So we have 3 tensions. We have the tension T2 along the string S2, we have the tension T1 along the string S1, and we have the tension T'3 along the string 3. So notice that in this case T'3 is along the string but it's away from the point A. So let's represent the forces on the node A. We have the tension T1, tension T2, and tension T'3, and let's represent these forces. So we're done with also step number 1. So suppose that this is the point A. This is the x-axis, y-axis, this is the tension T2, this is the tension T'3, and suppose that here we have a support like this. This is the string, and here we have the angle alpha, and this is the tension T1. Okay, and we know that the value of T2 is given by 2 newtons, the value of T prime 3. Okay, let's keep it. Okay, so these are the forces. Now here there are missing parts from the exercise, let me add them. Okay, part 3, let's say, determine T1, the magnitude of the T vector. Part 4, deduce alpha. Okay, so in order for the exercise to be complete. Okay, so we are also interested in applying Newton's second law. We have done with step number 1, which is listing the forces, and we are done with choosing a reference system. We are in part 3. Let's proceed to the next part, to the next step, which is projecting the forces. So if this is angle is alpha, so this is pi by 2 minus alpha, and this is alpha. So let's start by the force T2. T2 is completely lying on the x-axis, so T2x is T2 plus T2, and T2y is 0. As for the force T prime 3, we have that T prime 3x is equal to 0 because it's completely lying on the y-axis, and T prime 3y is equal to plus T prime 3. Now, as for the force T1, we have that T1x, it's pointing in the negative direction, so it's minus T1 cosine alpha, and T1y is equal to plus T1 because it's pointing in the positive direction of the x-axis, cosine of pi by 2 minus alpha, which is equal to T1 sine alpha. So T1y is equal to T1 sine alpha. Now we are ready to deal, okay, we have done projecting the forces, we are ready to deal with sum of forces is equal to MA. So let's say at equilibrium, for point A, because the node A is considered as a point, so we will say that the sum of forces is equal to 0 vector. On the left hand side, we'll write the different vectors that are acting on A, and they are given by T1 plus T2 plus T prime 3, and on the right hand side we write the 0 vector corresponding for the condition of equilibrium. Now let's project these forces. So this is a vectorial equation consisting of 3 vectors, so we cannot deal with it as we deal with the equation consisting of 2 vectors. So we need to project along the x-axis and along the y-axis. So projection along the x-axis. So in this case, we drop down the vector quantities, and each vector quantity will carry the label x. Then we have T1x plus T2x plus T prime 3x equal to 0. And we have determined previously these values. T1x is equal to minus T1 cosine alpha, and T2x is equal to T2, and T prime 3x is given by T prime 3 equal to 0. Now let's study the type of this equation before we proceed to the projection along the y-axis. Notice that the first unknown is given by alpha, and the second unknown is given by T1 because they are asking me to calculate T1. So this equation at least contains 2 unknowns. The value of T2 is given to be 2 newtons, and t prime 3 we have determined, which is equal to t3. Now the value of t prime 3 is equal to t3 because the string is inextensible. So usually this statement they give it half a mark. Then the value of t prime 3 is equal to also 2 newtons that we have determined above. Now t2x, okay, let me check something. How come? No, sorry, t prime 3x is equal to 0, so no need for this. So referring to this equation, we can see that we have two unknowns t1 and alpha. So in this case, this equation is not sufficient to determine t2 and alpha. So we need to project along the y-axis and simultaneously solve for t1 and alpha. Now let me replace the value of t2. So here we have that minus t1 cosine alpha plus 2 is equal to 0, which means that t1 cosine alpha is equal to 2. Or let me say, let's keep them as an unknown. So t1 cosine alpha is equal to t2. Now let's project along the x-axis. Sorry, y-axis. Now in this case we have that, okay, this is the vector equation. Oh, we drop down the vectors and each vector quantity will carry the label y, t1y plus t2y plus t prime 3y equal to 0. Now t1y is equal to minus t1 sine alpha plus t2y is given by 0, and t prime 3y is given by plus t prime 3, and as I have said previously that t prime 3 is equal to t3, an extensible string. So here we must have a minus sign somewhere. So notice that here t prime 3 is pointing in the negative direction of the y-axis, so it's minus. So in this case t1 sine alpha minus t3 is equal to 0, then t1 sine alpha is equal to t3. Now this is the first equation and this is the second equation. We need to solve simultaneously for t1. Then t1 cosine alpha is equal to t2, and so from this equation we can say that cosine alpha, so how to deal with such type of equations that include sine and cosine. So from the first equation we extract the cosine, from the second equation we construct the sine, then we use the famous equation that cosine squared plus sine squared is equal to 1 for the same angle. So sine alpha is equal to t3 divided by t1, and cosine alpha is equal to t2 divided by t1, noting that t1 and alpha are the unknowns. So cosine square alpha plus sine square alpha is equal to 1, then t2 divided by t1 to the power 2 plus T3 divided by T1 to the power 2 is equal to 1, which means that T1 square is equal to T2 square plus T3 square. The value of T2 is given by 2 to the power 2 plus T3 is 2 to the power 2. So this is equal to 8. Then if T1 square is equal to 8, then simply T1 is equal to plus or minus radical 8, but we are interested in the positive solution, which is equal to 2 radical 2 newtons. Then T1 is equal to 2 radical 2 newtons. And in part 4 they are telling me to deduce alpha, and by deduce it means that we need to test the previous part. In the previous part you have determined T1, and T1 for example and alpha are related via the following formula, that T1 cosine alpha is equal to T2 from equation 1. We are solving for alpha, then cosine alpha is equal to T2, which is 2 over 2 radical 2, which is equal to 1 over radical 2, which is equal to radical 2 over 2. And note that cosine alpha is a dimensionless quantity, so in this case the value of alpha is given by 45 degrees. So alpha is equal to cosine minus 1 of radical 2 over 2. Okay. So in the next part we will introduce the dynamics. Okay, so that's it for me in this video, guys. In next part, part 5, we will introduce the dynamics at the level of Newton's second law.